Welcome to the third lecture on kinetic theory of gases. Today we will recapitulate what we had talked about in the last class. I had asked you to verify the kinetic whatever information we obtained from the kinetic theory of gases, and I hope you were able to do so. So, anyway, we are going to proceed and see what we have gathered till now and proceed a little further. So, what we have got from the kinetic theory of gases, we have derived a relationship of pressure, and from this equation we can see that pressure, which is a macroscopic property of a gas, can be related to one of the microscopic properties of the gas, which is derived from the kinetic theory of gases, and that is the average value of the square of the molecular speed. So, what we can see from here, the pressure is proportional to the number of molecules present in the system per unit volume, and it is also equal to the average translational kinetic energy of the molecule. This tells us the pressure of the gas can be increased by increasing the number of particles per unit volume. That means, if you are increasing the number of particles, the number of particles striking the walls will be increasing, and hence the pressure exerted by the gas will be increasing. This also tells us that pressure also can be increased by increasing the molecular speed or the kinetic energy of the molecule. What does that mean? That means, if I increase the speed of the molecule, the number of striking with the wall also increases. So, number of collisions increases with the wall, and that also increases the pressure of the gas. So, the next one, this is the next relation which we have. Pressure we have related to the kinetic energy of the molecule and compare it with the pressure from the equation with that of the equation of the ideal gas law. Now, what is the relation which we have? This is the pressure relation which we had, and now we have related that to the temperature of the system. So, the temperature is a direct measure of the average kinetic energy of the molecule, that we have seen. How we have seen? We have seen by the following equations which we had derived in the last class. What we had seen? We have derived what the pressure is, and after the derivation of pressure, which is in terms of the root mean square velocity of the molecules, and then we had this ideal gas law, which where you have P V equal to nRT. Here we have the definite molecules of gas with a definite mass and occupying a definite fixed volume. Okay. So, the volume of the gas is fixed. So, if the volume of the gas is fixed, depending on the number of molecules which are present in that definite volume, we get the pressure relationship in terms of the root mean square velocity of the particles. Now, from the ideal gas law, we derive another expression for the PV, which is we are manipulating the term N, the number of moles. Number of moles is nothing but the total number of molecules present divided by the Avogadro number, and again we have a relationship between R and the Boltzmann's constants, which is R is the gas constant divided by the Avogadro's number gives you a new parameter known as the Boltzmann constant. This is how we can put the PV equation from the ideal gas law. So, from ideal gas law we have got this PV, from the kinetic model we have got this PV. So, we equate these two PVs. If we equate these two PVs, what do we get? We get the half m c square equal to 3/2 kT, okay, where what is the c, or we can sometimes we write v also. This is the root mean square velocity of the particles. So, what we have just now got is the expression of the half mv square or mc square equal to 3 by 2 kT, and kT where K is the Boltzmann constant, T is the temperature in absolute temperature scale, in Kelvin scale. So, what we have got from here? We have got for n number of molecules in a cubic container of volume V, we can write for if K is the average kinetic energy of one molecule, then for n molecules the total energy will be n into K, and this K expression we are replacing by 3 by 2 kT. K is the Boltzmann constant. This we can rewrite in terms of K being equal to R by Na. So, we can replace this and rewrite in terms of the expression of RT. So, I hope you can understand this, what I have substituted here. This is R by N. So, R by N is this, and then N by Na is nothing but the number of moles. So, I get R and number of moles. So, this is the another expression of the translational energy of a molecule from the kinetic theory of gases. Now what I today wanted to discuss is about the equipartition of energy. What is the mean energy or of kinetic energy of the particles? It states, the equipartition states the mean or the average kinetic energy of every degree of freedom of molecule can be given by half kT. kT is nothing but the kBT. What is kB is the Boltzmann's constant. So, if I have say the number of degrees of freedom is F, then the translational energy of the molecule will be nothing but the number of degrees of freedom into half kT. So, the mean kinetic energy per molecule can be given by this, and the mean kinetic energy per mole can be given by the same degree of freedom multiplied by the R. Okay. So, this is what we have, but what do we really understand by the equipartition of energy is what I am going to discuss today. And for that, what we need to understand when we are talking about the translational kinetic energy out here, the average translational kinetic energy, what is it that is contributing to the total internal energy of a gas? Let us see what it is. We will come to this later. So, what we are seeing is the total kinetic energy is the sum of the kinetic total internal energy of a gas. This is what we are going to be discussing right now, is the equipartition of energy right from the beginning of the concept of internal energy of a gas, right. So, the internal energy of the gas is nothing but the summation of the kinetic energy of the gas, the kinetic energy when the center of mass of the molecule is moved. That is what is going to be contributing to the translation form. Then you have the potential energy associated with the intermolecular forces and or potential energy associated with the intramolecular forces. Intramolecular, within the molecular forces which is existing, intra is between the molecules, the forces which are existing. So, what we are looking into? We are looking into one kinetic energy component and two potential energy component, and what are these what are the components which is, what is the energy which is contributed to the kinetic energy, what is contributing to the kinetic energy of the molecule. And what we are talking about? We are talking about the center of mass of the molecule being moved when we are talking about a translational movement. Okay. So, what happens when you are talking about the potential energy? Potential energy, if I talk about inter is nothing but the repulsive forces which is going to be equal to the repulsive forces which is going to exist between the molecule when the separation of the two molecules are smaller. This separation, when it increases, then the you have the intermolecular forces acting as attractive, and this is how you represent in the repulsive and the attractive forces. At low temperature, what happens? Low temperature, the average kinetic energy is small. Low temperature means the speed of the molecules are going to be less, and if the speed is less, the temperature of the total temperature of the system will be lowered. So, at low temperature, the average kinetic energy is small. The molecules can form bonds or in bonded states, and hence what happens? That means these the attractive forces are going to be in place. The intermolecular forces which are attractive in nature will be in force. So, in play. So, what we will have? We will have a negative value of the internal energy, and this will give rise to, say, condensation of forming a gas forming into a liquid or a solid. So, what is contributing? So, the attractive forces are contributing, giving rise to a potential energy contribution, where you have the kinetic energy very small at low temperature. So, potential energy dominates, and the potential energy is negative because of attractive forces between the two molecules, and this is going to give rise to condensation or bond formation or bonded states. At high temperature, what happens? At high temperature, obviously the temperature is increased, so the kinetic energy of the molecules is going to increase. So, the large kinetic energy, what happens? The internal energy increases, becomes positive, and in this case it has sufficient energy to break up the bonds or the attractive forces between the molecules, and they behave like a gas. So, this is what we are looking into when we have high temperature, we have the kinetic energy contribution at the large. So, you understand, when we are talking about the translation kinetic energy, we are talking about a molecule where only translation mode is contributing to the total energy of the system. We are not talking about the intra or intermolecular forces. What happens when the potential energy of these two, whatever you are having is attractive and the repulsive forces, the energies potential energy becomes minimum. At this point, if you remember the potential energy curve, it is a potential energy curve is like this something. Then we have a minima here, and this is the at the minima of the potential energy. What you have? The atom starts vibrating like a spring. So, this is what we are having in the background. Now, let us see what the degree of freedom means and what is actually the concept of equipartition of energy. The degree of freedom for a dynamic system is the number of directions in which it can move freely. Okay? The number of directions it can, it's actually a spatial coordinate by which we can describe this configuration as well as the position of the system exactly. Okay? So, it is a number of coordinates we require to describe the position is what is important when we are talking about the degree of freedom. Am I clear? It is actually in the when we say the degree of freedom in this concept of when you have energy distributed in the degrees of in various forms, we say in which form the energy is stored is another form of describing the degree of freedom. Any type of motion that contributes to a quadratic in a general coordinate to the internal energy is called the degree of freedom. Any type of motion that contributes a quadratic you may understand it is a square, it contributes a quadratic to the internal energy is called the degree of freedom. If I talk about a single molecule, when I have a single molecule, what are the forms of motions we can look into? See, we are looking into the degree of freedom is the number of directions in which it can move freely, or it is the number of coordinates required to describe the position and the configuration of the system. So, I need to know the number of coordinates which is required to pinpoint the system which we are talking about, its position and its configuration. Okay? So, the single molecule, what are the motions it can undergo? It can undergo 3 translation degree of freedom. what does 3 translational degree of freedom mean? Translation means along x, y or z direction. So, the center of mass can move along the x, y or z. When the center of mass moves along these 3 axes, we say that they are along the 3 vibrational modes. Similarly, it can rotate along a axis. So, along 3 axes we can have 3 rotational degrees of freedom, and then we can have internal degrees of freedom associated with the atomic structure. That means, we can talk about the vibrational mode of energy. These, for understanding this rotational and vibrational mode, you need to understand the quantization of energy. That probably will not be part of the course, but understanding that energies are quantized and you have to have sufficient energy to go from one vibrational state to another is what is supposed to require higher energy, is what you need to understand. So, first assumption what we are going to look, how the internal energy distributes itself along the n molecules. Each independent degree of freedom has an equal amount of energy. So, each degree of freedom will have equal contribution, and that contribution is half kT. This equal division of energy is called the theorem of equipartition of energy. So, for each independent degree of freedom, we have talked about translation, we have talked about rotational, we will talk about other vibrational modes, but what we are talking about, each independent degree of freedom has what is the contribution of energy, has 1 by half kT. So, in general, a degree of freedom refers to an independent means by which a molecule can possess energy. So, it is a degree of freedom can also be referred to the independent means by which a molecule can possess energy. So, why I say this? Independent mode, independent means of by which a molecule can possess energy, because I see that each of the modes I am associating with has 1 kT, half kT associated. So, if I look into a simplified version of it, then according to the kinetic theory of gases, we had, this is the expression of half mv square, or this is the root mean square velocity, it can be represented by c or v square equal to 3 by 2 kT. So, this can be applied to each direction. So, if I have x and y z direction, then each translation degree of freedom contributes equal to the energy of the gas, the generalized statement of the equipartition of energy. What I have 3 degrees of freedom, 3 translational mode of freedom mode. So, that is 3, and into what I have per degree of freedom, I have half kT associated. So, the total energy which associated will be 3 by 2 kT. So, each degree of freedom contributes half kT to the energy of the system. Which possible degrees of freedom in addition to the associated with translation arising from rotate, this is associated with only the translation, additional may arise from rotational and vibrational modes of the molecule. So, if I take an example of a monoatomic gas, monoatomic gas means it has one molecule, right. When I add energy, how is going to, we have said that how it is going to store the energy is the degree of freedom we need to know. How, if I put some energy, how it is going to store the energy. When energy is added to a monoatomic gas, suppose it is contained in a fixed volume. So, volume is fixed, all the gas energy goes to increase the translational kinetic energy of the system. When you are having monoatomic gas means we are talking about one molecule or one atom per molecule. So, whatever energy you put, it is going to go and increase the translational kinetic energy of the gas, right. So, now you understand why we were always talking about the average translational kinetic energy when we were talking about the kinetic theory. There is no other way it can store the gas. So, therefore, the total internal energy for n molecules of a monoatomic gas will be equal to just n times the kinetic energy associated with each of the molecule along the 3 translational modes, and that will be 3 into half kT, that is 3 by n kBt. This is the total number of molecules which we are associated. So, what we can see, the internal energy is equal to the total translation energy for a monoatomic gas, and that is equal to proportional only to the temperature. And since it is a constant volume system, I can say the amount of heat which is absorbed is equal to the change in the internal energy, which is nothing but n Cv dt from the expression which we have. What is Cv? Cv is the specific molar specific heat. So, molar specific heat, if we can justify for a constant volume, the molar specific heat into the change in temperature to into the total number of moles is the amount of energy or heat which is absorbed. This applies to all ideal gases, not just monoatomic gases. Now, so solving that, Cv equal to if we can write that what will the internal energy look like, the expression of internal energy. You see, you put the expression of Cv, Cv gives you 3 by R, 3 by 2 R. So, you can get what for this what you have is the internal energy change in terms of the per mole of the gas. So, this is something which you can solve for if you know the degrees of freedom. This applies to all ideal gases. This is what we have done through experimental observation, whether the internal energy is actually, see, the Cv is a response function, we can measure Cv. So, if we can measure Cv and we know the value of the Cv which is measured, and then we can see what is the internal energy change. Experimentation has found out that we have a good agreement if we follow the kinetic theory of gases and the equipartition theorem. So, next we go into a complex molecule, where a complex molecule means you have more than one atom associated with it. So, complex molecules, with complex molecules what happens? There are internal energy will be contributed not only by translational energy, but also because of vibrational and rotational modes. The complex molecules, So, the complex molecule we have the contribution to internal energy by number of things. What are the contribution we can have? We can suppose this is the complex molecule, just we are talking about only having two atoms associated. What I can do? I can move this the center of mass from one point to the other. So, this is by changing the translation contribution through change in the translation motion of the center of mass. I remove this entirely. And what else I can have? I can have the molecules rotating along the axis. Suppose I have this molecule along the y axis. Now, I rotate along x or along z. Then you have some modes which is going to contribute to each of the movement along this x and z. Let us consider, since the molecule is along the y axis, the contribution in the rotation along this is minimum. We say only two modes are contributing. See, here when we are talking about translational mode, we can have the molecule moved, the center of mass moved toward the x direction, towards the y direction, towards the z directions. So, I get three modes from the movement of the center of mass along the translation mode. Now, when I talk about the rotational mode, if I have taken this molecule as a two molecule system and I am rotating along the molecule is along the y axis, then I can rotate it along x axis or according to z axis. These two contributions will be much more than along the y axis along which the molecule exists. So, next we can think about Next we can think about a vibrational mode. What is this? When you are having the molecules which are vibrating along the axis, this vibration, this kinetic energy, and thus there is kinetic energy, potential energy associated with the vibration. So, that what are the different modes we have? We have the three transitional motions, 3 degrees of freedom, 2 rotational modes, because one we have taken along the molecule, the axis y z, y is along the molecule. So, we have not taken the contribution, neglected the contribution along that. So, we have 2 degrees of freedom along for rotation, and we have vibrational contribution, that is going to be 2 vibrational degrees of freedom associated with the molecule. So, if I have a monoatomic molecule, then the total number of molecules a degree of freedom I know is 3. Only for the when the center of mass is moved along the translational mode x, y, z, 3 modes. When I have a diatomic molecule, the degree of freedom is 3. 3 for translation, the center of mass of the molecule moving x, y, z and z direction, plus 2 along the axis along which it is rotated, taking the molecule to lie in one particular axis. Suppose it is y, and we have taken x and z as the rotation along which we are looking into. So, similarly, nonlinear and trilinear molecules will have different degrees of freedom, which we can calculate knowing the contributions of each. So, now we need to verify whether a system which we are doing, finding out the energy associated with the internal energy associated with the molecule, whether which we have equated that to the system is proportional to the CV of the system, that is a molar specific heat at constant volume. Since this being a response function, we can measure that. So, if we measure that, it is found that whatever we have found for the monoatomic or diatomic gases is more or less agreeable to whatever we find using the kinetic theory of gases or equipartition theorem. And at low temperature, you can see that the diatomic molecule acts or behaves like a monoatomic gas, and it is CV is equal to 3/2 R. So, you can see how the CV is varying in terms of the value of R, whether it is 3/2 R, 5/2 R, 7/2 R. 7/2 R means obviously the vibrational contribution is there. 5/2 R means two rotational contributions and 3 translational modes are there, and here means only translation 3 translation modes are contributing. So, you can see when you have a translation, only 3 modes are active. When you are having rotation, we have 5, and when you have vibrational, you have 7 modes which is active. So, this is what we have, which is experimentally seen, how CV changes with temperature, and with you see the temperature scale, it is around 100 that you see this transition. When a molecule is at 1000 degrees centigrade, you will see the rotational contribution, and when it is more than 10,000 the degree Kelvin, then you will see the contribution of the vibrational mode. So, if we can summarize, at room temperature, the value increases to CV equal to 3/2. This is consistent with the addition of adding rotational energy, but not vibrational. At high temperatures, the value increases CV equal to 7/2, that is the contribution is here we include the vibrational energy as well as the rotational and translational. For molecules with more than 2 atoms, the vibrations are more complex. Number of degrees of freedom, the number of degrees of freedom is larger. The number of degrees of freedom available for a molecule, the ways which they can store the energy, this results in higher values of molar specific heat. Did you understand what I said? The more degrees of freedom available for a molecule, the more number of ways we can have the energy stored. That means that will give a higher value of CV, because CV is nothing but Q equal to N CV dt. So, CV is a direct amount proportional to the amount of heat which is absorbed. So, we can have this increase in energy associated with the increase in the specific heat. So, summarizing this, the equipartition theorem, we will talk about the various distribution of energy and distribution of speed of molecules in the next class. Thank you.